Good morning, and thank you for coming and attending our webinar. My name is Carrie Ann Simpson, and I am the Director of Sales for North America for VUV Analytics. This morning, we're going to provide a general technical overview of the vacuum ultraviolet, the VGA-100 gas chromatography detector. I will do about 30 slides to give you an introduction to the technology. I will then take questions. If you have questions on the left side of your screen, in the lower left-hand corner, you should see a section where you can enter questions. Please feel free to enter those questions as we go. I will attempt to answer as many of them as possible. And anything that I don't get answered during the presentation, I will follow up with you at a later date. When I'm finished with questions, I do have some additional application slides that I can provide that may go past that 45-minute time frame. You're welcome to stay and ask any questions about those that you'd like. Just a little background about me. My background is chromatography. So if you've got, I know that there are a few spectroscopists on the line. If you've got sort of tougher spectroscopy questions, feel free to ask those questions. I may not be able to answer them, but I will get back to you if I can. So to begin, we should talk a little bit about what vacuum ultraviolet is. The vacuum ultraviolet is actually a range of the electromagnetic spectrum that many of us as chromatographers are not familiar with. We're very familiar with UVA, UVB, UVC. As chromatographers, we're used to working in the UV visible range above 190 nanometers, but working below that is not a place that we're familiar with. What you'll notice from this slide is the vast majority of the electromagnetic spectrum has been commercialized up to this point, but not the vacuum ultraviolet range. So one of the questions we get is, why didn't someone do this before? And the answer to that question actually is that we've pretty much been told, all of us as analytical chemists, that the energies associated with single bonds are restricted to the vacuum ultraviolet region, and the experimental difficulties associated with the vacuum ultraviolet are significant. And as a result, no further discussion will be devoted to this type of absorption. So Dr. Skug, who most of us are familiar with in analytical chemistry, basically told all of us in chemistry that vacuum ultraviolet chromatography is not really possible. The reason that VUV Analytics has gotten into this space is that the gentlemen that founded our company are not analytical chemists. They're physicists, and they have come from the semiconductor space. Previously in their careers, they utilized vacuum ultraviolet reflectometers to measure thin film dielectrics in the semiconductor space. And they took some of that technology and created this detector. They then took it to the researchers at Dow Chemical in Freeport, Texas, at which point they said, you know, this would make a great gas chromatography detector. And so the gentleman that started our company actually went back to the lab and Googled gas chromatography. And here we are a couple of years later, and they have developed this interesting new gas chromatography detector. So why would we want to use vacuum ultraviolet spectroscopy? Well, it's very simple. Virtually everything absorbs strongly in the vacuum ultraviolet range. We are very able to see small molecules. We're looking at pi star, sigma star transitions. And in fact, with even smaller molecules, we start to see some vibrational structure. And so not only does everything absorb, it absorbs strongly and with very unique spectra, which is a little bit different from the liquid chromatography above 190 range that we're used to seeing, where spectra is not particularly distinct and prone to issues based on mobile phase effect. Although it's not without its challenges. Because virtually everything absorbs strongly in the VUV, we see things like water and oxygen. And because water and oxygen are ubiquitous in our environment, it makes the detection challenges of this technology fairly difficult. And that's one of the reasons that this technology has not been commercialized up to this point. So the detector has been called by Dr. Harold McNair. He pointed out to us that this is actually the first new detection schema in 30 years. If you consider that even some of the BID technology has been in the literature as far back as 1960, and while mass spectroscopy has made advances over the years, it's been around for a very long time. It's a fairly mature technology. And so this is really truly the first new GC detector technology in 30 years. This is what it looks like. The vacuum ultraviolet detector, the VGA-100, is now available to the scientific community. We are looking at absorption spectra between 120 and 240 nanometers, which gives us some unique capabilities and an orthogonal separation. The instrument is very selective. It can give us clear compound identification. It will allow us, because of that clear compound identification and the fact that it's an absorbance spectrometer, it gives us the ability to deconvolve co-eluting analytes very, very easily, and to use what we call spectral filters to reduce or eliminate matrix contribution. It's very sensitive. We are in the low picogram range for most compounds. One of the biggest benefits of this technology is the ability to actually see clear and easy isomer differentiation. We actually are able to see spectrally differences between cis and trans isomers, positional isomers, but not chiral compounds. It is not destructive. We're not doing any kind of ionization, and so we're not limited by compounds that are easily ionized or by compounds that maybe fall apart in our source. It's a very fast detector, so we can do up to 100 Hertz sampling, which allows us to be amenable to GC by GC. We don't have issues with flow rate, and so we see this detector as being a good technology for flow modulated GC by GC. It is absorbance detection, and so it provides a predictable linear response. Simple first principle detection makes calibration burdens much lower. It's very reliable and easy to use. One of the things I'll show you is that we don't actually use vacuum pumps. This is one of the common questions with regard to this detector, where customers say, when you're doing vacuum ultraviolet, how can there not be vacuum pumps? I will show that as well. One of the things I should point out is that nature has done us a favor in that helium, hydrogen, and nitrogen work very well as carrier gases because of the many components that do absorb in the vacuum ultraviolet range. It's been sort of a favor of nature that helium, hydrogen, and nitrogen and argon don't absorb well or not at all in this range. So this is what the detector looks like. There's a nice block diagram on the right. What you'll notice is that we have the source module on the left. This is a standard deuterium lamp, and a detector module on the right. Both of these modules are pumped down at the factory and replaced with dry nitrogen. The air is replaced with dry nitrogen, and the modules are sealed off. And then we use a bit of a curtain gas to maintain the atmosphere free of oxygen and water. Flow cell between the two modules with magnesium fluoride windows. You'll notice the gas chromatograph at the top. The sample passes through the flow cell and then back the outlet port. It does connect easily to any GC. We don't have a specific relationship with any specific gas chromatography vendor. We use adjustable feet on the detector to move it up and down, and it connects through your mass spec port. And so it's just a simple GC detector connection. We don't use any kind of sample ionization. We do use a bit of a makeup gas if required in the flow cell, and the flow cell itself is about 80 microliters. It's 10 centimeters long and about a millimeter in diameter, excuse me. And then it's silicone protected. Again, we don't use any vacuum pumps. The instrument is pumped down at the factory, and so there's no requirement for vacuum pumps. Again, the wavelength range from 120 to 240 nanometers with up to 100 hertz acquisition. You'll notice that we get what we call a total absorbance chromatogram, much like you would, again, with any other three-dimensional type data where you're taking the sum of the spectra. And then we can also use spectral filters to extract absorbance chromatogram. The software that we use is our software. We take a start-stop signal from the gas chromatograph, and as with many detectors, mass spec included, the power of the detector really has to do with what we do with that data after it's collected. So we'll talk a little bit about what we get from the instrument. What you'll notice here is that we have a total absorbance chromatogram, and with the different peaks, you'll notice that under each peak, you have a full VUV spectra. And these spectra are specific to the compound. As with mass spec and with photodiode array detection, we're able to do a library search. What you'll see at the bottom are two spectra overlaid. One is the collected spectra and one is the library spectra. And immediately above that, we're looking at the residual. And you'll notice that while it seems a little bit noisy, the range is quite small. What you'll notice on the left, and this is interesting and very powerful to this detector, is that the compound that we've chosen is actually the first compound that comes up on the list. And this is pretty typical with this detection, and that's different from mass spectroscopy in that often when we're looking at a total ion chromatogram, our compound of interest is the second, fourth, fifth compound. With this detector, it is more often than not the first compound. And what you may also notice is that the compounds that come after that first compound actually are very similar in class. So unlike with a mass spectra where you're collecting based on the M over Z, you may have multiple compounds that have very little in common that give the same M over Z. We don't see that with this detector. So what you're seeing here is on the right, where we've actually taken a compound that's very similar to the compound of interest, and we forced it to misfit. And what you'll see is that while you have compounds that look very visually similar, they're actually very easily distinguished in our fitting routine. And 99 times out of 100, we will not misfit those two compounds. So we'll talk a little bit about what we call spectral filters. Essentially, what a spectral filter is the separating compounds based on a range of wavelengths. So if you'll notice on the left, the linear alkane spectra pretty much ends about 165 nanometers, whereas our aromatic spectra gives us very strong response above 165 to 200. And you'll also notice that within class, so the linear alkanes have very similar spectra, and the aromatics have very similar spectra. And so this allows us to separate based on class and to, in fact, eliminate a portion of the spectra to reduce matrix effect. So what we've done here is we've attempted to pull away alkanes from olefins by using these spectral filters. So at the top, you notice that we're looking at 125 to 175. Then at the bottom, we're looking at 175 to 205. And we see almost no contribution, or essentially no contribution from the alkane. And that allows us to focus in on the olefin. Here's another example of that in a gas application where the customer was interested in looking at hydrogen sulfide contaminant in a phosphine stream. And what you'll notice is that hydrogen sulfide has a very strong absorbance response at about 140 nanometers. And so if we take a very small portion of the spectra, and you'll notice the green trace is 138 to 142 nanometers, we're able to pull that H2S out of the phosphine tail. We'll talk a little bit about spectral deconvolution. So this is simple Beer's law stuff. Total absorption is proportional to the product of the concentration and the absorption cross-section. And so coelution is simply a sum of these products. So we're able to use simple linear regression to deconvolute the compounds. Essentially, this allows us to reproduce what the baseline resolved constituents would look like if they were not coeluting. So what you'll notice here on the left is we're looking at a peak that's been identified as benzene, but the software looks at that and says, you know what, there's something else there. If I look on the left side of my spectra, there's clearly some difference there. And so the software attempts to improve that fit by adding in additional compounds. And when we add in that 1-methylcyclopentene, we get a much better fit. We're then able to deconvolute and give accurate determination of the coeluting compound. I would say that this is arguably one of the most powerful attributes of this detector, and that's our ability to look at different isomers. And it's a clear advantage over mass spectrometers. I think that all of us know that when we're looking at two compounds that are positional isomers, cis-trans type isomers, that we don't really see any spectral differences on the mass spectrometer. And so if we have instances where not only do we have isomers, but those isomers coelute, this technology is very powerful, because what we see is that many isomers have a unique absorption spectra. And so we're able to see the fact we certainly have a common class, but we are able to see there on the lower wavelengths some insight into bond location. This is sort of the classic example, OMMP xylene in the hydrocarbon world. It's something that is a challenge for customers, and we can see clear spectral differences between those compounds. So these analytical figures of merit actually came from a paper that was published by Dr. Kevin Shug at the University of Texas in Arlington in Analytical Chemistry late last summer. And so if you'd like to dig in a little bit deeper, that paper is an excellent resource. We do think actually that some of these would be improved on some of the newer models of the instrument. But what you see is that spectral resolution is excellent. On the low end wavelength, we're looking at about 1/4 nanometer resolution, and on the high end, we're at about 1/2 nanometer. And so in general, we say less than a nanometer of resolution. Limited detection is less than a nanogram on column. And the dynamic range is excellent, at least 4 orders of magnitude. We do have some customers who will move from the main absorbance peak to a secondary absorbance peak when the first one overloads, and they can get more than 7 orders of magnitude. And the reproducibility, you'll notice, is excellent, less than 2%. So what we have essentially is the world's first vacuum absorption detector for gas chromatography. It is a very powerful new detection that provides orthogonal separation capabilities. We can clearly unambiguously identify compounds and reduce matrix contributions using spectral filters. We can see the difference between isomers with good sensitivity. The fact that it is non-destructive allows us any number of potential hyphenated applications down the road. It is a very predictable and linear response, as are many other absorbance detection techniques. And it's very easy to use. We're not using any kind of vacuum pumps. It fits on any gas chromatograph. It allows you to easily use carrier gases like hydrogen, for example, which can be a challenge with mass spectroscopy. And it's like every other UV detector out there. It's, a simple 2,000-hour lamp. We see this detection really as a new tool. And what we know is that new directions in science, Dr. Dyson likes to say that the new directions in science are launched by new tools much more often than by new concepts. We're all very familiar with mass spectroscopy. We're all very familiar with FID and TCD. And this detector allows us the ability to see things that we've not been able to see before. And so it's in many ways complementary to FID and mass spectroscopy in that it's giving us information that we didn't have before. There are clearly some places where we are superior to mass spectroscopy in terms of ease of use, in terms of spectral identification of isomers, in terms of sensitivity on very low molecular weight compounds. The one application of interest that we've seen quite a lot is formaldehyde, for example. That's an underivatized application. So low molecular weight compounds are no problem for us. So there are clearly places where we are superior to mass spectroscopy. There are clearly places where we are superior to FID. But we see it very much as a complementary technique and in some cases competitive technique to mass spectroscopy. So I'll take a look at some of the questions right now. So the first question I have is, does the detector eliminate the need for internal standards to differentiate your cis and trans isomers? Possibly. In my opinion, I think that's going to depend on your laboratory practice, but that's certainly something that we could discuss further. We do have customers that are eliminating the need for internal standards, so yes, it's possible. The next question is with regard to how many compounds we have in our library right now. Well, I can tell you that the compound library compared to, say, mass spectroscopy is small. We have about 1,000 compounds, and that grows about 50 a month, 30 to 50 a month. We would hope as this instrument becomes used more in the industry that it will grow much more rapidly. We know that customers in the academic world are more likely to share those compounds than those customers in the industrial world. But we're certainly open to both, and we are certainly going to share all of the compounds that we have available. Okay, so the next question is, what are the electrical requirements of the detector? It is 120 or 220 depending on where you're at. The instrument is set up for either. It really is a matter of changing the plug. Okay. What is the detector's overall size, weight, and power requirement? So the size of the detector, give me just a moment. I believe I have. Here we are. So the detector is 13 by 27 by 17 inches, and it's about 120 pounds. It is a very heavy detector, and the reason it's a heavy detector is that it's the internal workings of the instrument are set up on sort of an optical backplane. If you can imagine, the flow cell runs at about 300 degrees C, and then we need the optics to be maintained at about 30 degrees C. And so there's a fair bit of changing of temperature and expanding and contracting within the instrument. And so it's on an optical backplane to allow it to sort of float to ensure that the optics stay aligned and unaffected by vibration or those temperature effects. Next question is with regard to software. Does the VUV software operate the detector only? At this time, yes, it operates only the detector. We do see opportunities for working with other companies to take control of some of the gas chromatographs that are out there. We're in the process of doing that, but we have not yet. As far as interfacing with common GC operating software, for example, Agilent's OpenLab, We can export our data to OpenLab as a .cdf file. That's certainly a possibility. You can export the total absorbance chromatogram. You can export any number of spectral filters, but then you would be relying on OpenLab and the limitations of OpenLab and its capabilities with regard to data reduction. So the next question is with regard to temperature limits. I mentioned that a second ago. About 300 degrees C is the highest we can go. Dr. Whipple's question I don't quite understand, and so I will call you and discuss that further with regard to the isomer question. Nathan Kreisberg, your question with regard to what fraction of spectra can be uniquely identified from every other spectra in the database. Again, I think I'd like some clarification on that question before I dive into it. The detector cell is at ambient pressure. It is not essentially, we can see everything that comes through your gas chromatograph into the cell, but the cell itself is at ambient pressure, and what we're seeing is what's coming out of your GC. And so if you have an extremely high amount of water in your gas chromatograph, we will see that. If you're analyzing for oxygen, we will see that. But the detector cell itself is not under vacuum. How to account for strong water absorption? This is an interesting question. We actually have customers who are interested in using this detector to analyze for water, to replace other moisture analysis techniques. We can see water. So if you have samples that have a very high water matrix, then what we see is that you need to go to a column technology that actually can pull the water away from your compounds of interest. This is my favorite question. Can VUV be used in line with mass spectrometry? And the answer is we believe so. We've not done it ourselves. We've had a number of customers ask if that can be done. We view that as an engineering challenge, not as a detection challenge. We don't have to use that makeup gas flow, and so the flow coming out of the back end of the detector is going to be the same as what's going into the detector. There may be some challenges with band broadening because of the volume of the cell, but we just don't know. Okay, so with regard to measuring nitrogen, we can measure nitrogen, but nitrogen has a very poor absorbance cross-section. And so while we can measure it, we can only measure it at very, very high concentration. We can also see carbon dioxide, again, at very high concentrations. And I'd be happy to talk with you offline and show you some of that chromatography. We actually have some, and I may actually have some applications here if you stick around that show carbon dioxide. But we certainly can measure those two things. Have we done work with any cycloprenoic fatty acids? Offhand, I don't know about cycloprenoic, but one of the first applications that I will show here in just a minute are fatty acids, fatty acid methyl esters, and we can certainly talk about that. We have done some of that. Do common derivatization reagents contribute interfering peaks? Offhand, I don't know the answer to that question, but I will find out. There is not a separate charge for the library. The makeup gas that I mentioned can be anything that you choose. It can be hydrogen, it can be helium, it can be argon, it can be nitrogen. Maintenance requirements and maintenance done by the user. I believe that the vast majority of maintenance can be done by the user. One of the common questions that we get is what happens if I foul the flow cell? And the answer to that is it's a very simple thing. We actually disconnect the gas chromatograph and we allow ambient air to enter the instrument. We then open the shutter and allow VUV light to come in, and we essentially create ozone and do an ozone clean. We let it sit for 20, 30 minutes. We reconnect the GC, flush out the cell, and essentially the instrument is clean and ready to go. Depending on what your application is, you can do that every day. You can do that weekly. The lamp itself is a 2,000-hour lamp. It takes about 6-7 minutes to replace it. It's definitely replaceable by the user. We do find that for whatever reason, we believe it is because it is in this sort of inert nitrogen environment, that the lamps don't fail in 2,000 hours. They take much longer to fail. The manufacturer specification is 2,000 hours, so that's what we quote, but they tend to last much longer than that. Mr. Daly, with regard to pesticides, actually there's a very interesting paper that came out, again, out of Kevin Shug's laboratory at UT Arlington in the Journal of Chromatography A this past month that is specific to pesticides information. So yes, and it's been published. With regard to carrier gases, I don't know the answer to that question offhand. I can tell you from that with nitrogen as a purge gas, we're looking at 5.9, so same level of purity that you're typically used to. Okay, so with regard to the question about chiral compounds, again, we are not, so chiral compounds have the exact same electronic transitions as one another, and so we're not able to see the difference between chiral compounds. We have done some steroid hormones. Again, those came out of Kevin Shug's laboratory. I think there's an example in his paper that came out, the analytical chemistry paper last summer, that shows some steroid work, but it's not extensive. And I believe that was the last question that I can answer at this time. Additional questions?